John Park is the Product Management Group Director for Advanced Semiconductor Packaging at Cadence Design Systems. He has over 35 years of design and EDA experience, and he is focused on defining cross-domain solutions. So, John, we'll turn it over to you.
All right. Thank you, Ira, for the introduction. The title of my talk today is 3D-IC, or really 3D heterogeneous integration design challenges. And the outline I have for the next 30 minutes or so, 25, 30 minutes, is shown here. So I do have a couple of slides introducing and talking about our view of 3D-HI and chiplets and the whole world of kind of more than more. And then we'll go into some specific challenges around the ecosystem for chiplets and such. We'll then talk about the challenges facing package designers as they move to 3D-HI. And we will finish talking about the new challenges for traditional chip designers, ASIC and SoC designers, as they move into the world of 3D-HI. So to really kind of set the stage for and to explain kind of how we view this whole world of heterogeneous integration, I typically use this image here to explain our view of the difference between chiplets and bare die that we would see in a multi-chip module system and package. So the left-hand side of this picture shows what we used to do and will still continue to do with regards to designing multi-chip modules, a system and packages, which is really looking at the board and trying to make it smaller to reduce size, weight, and power. So taking the die out of the package components on the board and integrating bare die, typically on a laminate or ceramic substrate. We've been doing that for over 40 years now. That does not go away with 3D-HI, that will continue. But really the new part of the kind of the new trend of more than more is shown here on the right-hand side of that picture, and that is the trend to take monolithic chips and build them in a more modularized base approach, again, turning to packaging to aggregate the chiplets, which we'll talk more about coming up in the next slide. So it's really about it's a different way of building a system on chip or ASIC into these modularized chiplets. So it's really the disaggregation of a chip. And there's lots of reasons people are doing this, design cost at advanced nodes, die sizes. The modern SoCs are reaching maximum reticle limits. And when you build chips that big, anyways, they don't yield. So there's lots of reasons, including die size and improved yield, to move to this world of 3D-HI or 3D heterogeneous integration, which would also include stacking. So that's our view on kind of the system and package multi-chip module versus heterogeneous integration. Hopefully that clears up a few questions. This term heterogeneous integration, some people like to use it as a substitute for packaging. We don't believe it is a substitute for packaging. Heterogeneous integration actually looks at multiple different ways to aggregate those chiplets together, including the previous presenter talked about interconnect bridges, silicon interposers, bumpless integration, even thin film laminates. So the aggregation of chiplets into these 3D-HI packages is really considered a different process, and this is where the EDA design tools come into play. Is the planning, optimization, design, and verification of these heterogeneous systems. So I think it's important, at least for my next few slides, to understand that distinction between heterogeneous integration as a form of packaging into, it's really not, it's just a way of repartitioning a system or subsystem and then looking to different packaging technologies to actually aggregate them. So what this really means from an EDA tool provider perspective and how this breaks down regarding the previous talked about packaging technologies is we look to different design tools and different design methodologies dependent on the specific type of packaging that the user might be doing. So 3D packaging shown on the left there Of course, in the world of package substrate design, we've been doing heterogeneous integration forever. We didn't call it that. We called it system to package. And we've also been doing 3D stacking forever and ever. So to the world of packaging, integrating devices at different nodes, even different technologies, and stacking them vertically is nothing really new. There are some newer technologies, but which we'll talk about here in a second. But the left-hand side here, those are the types of what we would consider packaging technologies specific to the integration of multiple die or multiple chiplets in a packaging configuration. And that's a very unique set of design tools and methodologies and design skills required on the left-hand side. Moving to the far right-hand side, under the category of 3D integration, this is really where the world of 3D-HI is heading, in our view, and that is basically a solder-free or basically no solder bump connection. So people use the term hybrid bonding, copper-to-copper bonding, direct bonding. There's lots of different terms for it, but it's really about connecting macros, circuits, cores, full chips combining them typically in a face-to-face configuration using very small 1 micron sort of range hybrid bond pads between those. So it's a very different set of challenges as you're on the right-hand side here than it is on the left. The right-hand side requires more expertise in IC design. You're working with standard cells directly. You're working with down to the transistor level in the IC world. So it's a different set of tools, and we'll talk more about that coming up in the slides as you move to the world of 3D integration. And then sitting there in the middle, was kind of the hybrid world where designers use a combination of the two tools. So for example, ultra high density RDL has a lot of routing that's very similar to what you would see on a laminate based design, but it's built typically in many cases in an IC foundry. So the output of the tool is GDS or OASIS data because you're designing a wafer essentially. And so the layout tools might be tools shown on the left, but the verification tools would be something you would see on the right. So the formal verification of DRC, LBS, for example, would be required to tape out that fan-out wafer level packaging using ultra high density RDL. So same would apply to silicon interposers. It combines the two worlds of 3D packaging and 3D integration from a methodology perspective. And we'll talk more about that as we get into some of the challenges around these next generation of 3D-HI packages. So we're going to again start with the ecosystem, and we'll talk about some of the challenges for the package design teams, and then some of the challenges for ASIC designers. Starting with the first here, ADKs or assembly design kits. Some people call them PADKs. The concept here is in the world of designing ASICs. For the last well over a decade, we've used process design kits to start a new chip, and the process design kits would have all the information we would need as an ASIC designer to start to design our specific chip that we're designing. So that would include information about the technology being used, layer stackups. It would include libraries such as standard cells and IOs. It would certainly have all the rule decks to sign off on DRC, LBS, and metal fill. So we had a very good starting point when designing chips. As we move to this world of 3D-HI and the world of packaging, we historically have not had that nice set of data that we use to start a package design. It's a much more of an informal process to starting a package and taping out a package for that matter. So there are some people that talk about assembly design kits. We don't necessarily think that they're a complete ADKs. Most of the ADKs that you might hear about today are really focused on rule deck, so on the physical verification of DRC and LBS. And we think there's more components that should be added to that, such as design libraries for packaging. They would be different. They'd be mechanical structures, via structures for the discrete components, wire bond profiles, those types of things. but this is a topic that could take quite a bit of time to talk about, but it is an area that's a growing area in the world of semiconductor packaging, really driven by the foundries. And the key component is it will drive the assembly of your 3D-HI package, shown kind of in the pictures on the right-hand side here, to assure the layout person that whatever they're placing with regards to stacking chiplets or placing them side to side can actually be manufactured by the pick and place equipment that you would need to do in a high volume manufacturing flow. So assembly design kits. The second is really the availability of chiplets. Everybody likes to talk about chiplets, and it's a great concept. However, most chiplets today are designed in vertically integrated companies. So it's a closed ecosystem. So the large ASIC providers, they design their own chiplets. They don't necessarily share those chiplets to the whole world. They use them internally to take advantage of the higher yield and lower costs and more modular based approach. The original program that kind of kicked off this world of 3D-HI was, at least in our view, the DARPA CHIPS program, which kicked off about 6 years ago. And the vision of the DARPA CHIPS program was really to commercialize the world of chiplets and also come up with a standard interface, which is an important component to being able to standardize on these chiplets. So that's the view, to really have it almost like a PCB world where a designer can open a catalog and search through hundreds or thousands of chiplets, pick the chiplets they want, add their special sauce to that, and create their next generation of design. That's where the industry needs to go. The industry, in our view, is quite a ways away from being, having that catalog of chiplets. There are a few specialized companies that are providing chiplets. Cadence is also starting to provide chiplets, and more will come out as we move forward. And of course, a big requirement for that is the standard interface that users can use when connecting the chiplets. And the view in the early days was there would be one specific communication interface. We don't necessarily believe that's going to be the case, just simply because there are so many different ways of aggregating the chiplets or so many different ways of packaging them. So we believe it'll be almost like a PCB. There will be a couple dozen different interfaces. But we've seen, UCIe is the latest one that Intel and others are behind. The ODSA group is proposing a bunch of wires. Xilinx is created license-free the HBI spec, Open HBI, and of course Intel's also provided AIB in multiple license-free in multiple different supporting multiple different types of packages. So that we're making a lot of progress here, but we still think there's quite a challenge when designers move to this world of 3D-HI, expecting to have this huge catalog of available chiplets. We're still quite a ways away from being at that point. And then the final ecosystem challenge, and the previous presenter talked about this a little bit as well, is really the complexity of the design flows. So users want to have tight co-design or concurrent co-design between boards, packages, the chiplet designer, and that's from a planning and optimization perspective, implementation. There's all kinds of sign-off for thermal, electrical, physical verification. And so what happens is you end up with a tremendous number of design tools covering everything from that early stage planning through different tools for specific to the type of implementation that's going on, all the way through the timing tools and thermal and electrical. So the number of design tools grows quite significantly as you start to integrate the design teams across the chip package and board design domain. So and that of course you're bringing into these things. It's not just a digital world. There's you bringing in the RF design teams, the analog designers into this world of 3D-HI as well. So we'll talk more about the design tools coming up, but there are quite a number of specific challenges around those individual design tools as well. So Moving on to some of the challenges that our customers face from a traditional package designer's perspective. Previous speaker talked about this, the ability to plan, edit, and optimize across the chip package and board. There's a couple of tools in the industry today that allow that ability, kind of shown in the picture in the bottom middle there, to be able to optimize, for example, the pinouts so that the interconnect is optimized from the PCB up to the substrate onto the interposer and finally onto the chip. This is an example of being of working in that cross-platform, cross-domain environment across chip, package, and PCB, where ideally each of the design teams can come into this design tool and optimize based on their requirements for electrical, thermal, whatever it might happen to be. Typically, however, these tools do work at an abstract level. As shown in the picture here, you're not going to see down to the standard cell or transistor level of the chip, for example. You're going to have more of a black box, which today seems to work pretty well for a lot of the types of packages that we do, because it's really a task of optimizing the pinouts for connectivity and in some cases power. That's changing as we move forward. And then another important change for the package designer is they now need to run or provide a golden net list for the LVS, or the connectivity verification. So when we build these systems, they have to be validated from a connectivity perspective across chiplets, through interposers, onto substrates, and even out to the PCB. So having a methodology that, first of all, allows you to plan and optimize that golden top-level net list, but more importantly, be able to use that net list to sign off on LVS is a critical new step for the people moving from the world of substrate design into the world of 3D-HI. On top of that, there are some analysis challenges for package designers as they move to this world. It becomes like a small PCB. So signal integrity becomes very important in this. So you're validating from a compliance spec, the chiplet to chiplet interface. There'll be a spec for that, whether it's HIB or UCIe. There's a spec that says this is, basically the size of the eye, and you have an eye mask, and you have to make sure that there's not too much jitter and noise on the signal to validate from an electrical perspective, the chiplet to chiplet compliance. We have a lot of designers out there that want to do things like early stage pre-place and route, look at different levels of package integration for different chiplets. So the picture down here in the lower right shows that in one case, the high-speed SerDes are on the silicon interposer. To save some costs, maybe the interposer should be reduced in size, and perhaps placing the high-speed SerDes out on the laminate substrate. So designers want the ability to characterize that and make sure that they can meet their design spec, regardless of where the chiplet is placed in these multiple levels of packaging. And so there's some tools out there today that are based on the PCB technology that allow you to do that, using driver receiver models and parameterized interconnect models such as TSVs and transmission lines and those types of things. So signal integrity becomes very important for the package design team. Last but not least, for the package designer, as we move to true 3D-HI, there's more silicon content in the package. So obviously silicon interposers. We talked about ultra high density RDL, fan-out wafer level packages. So they're the types of designs being created by these design tools, which have historically done layouts for laminates and ceramics, changes quite a bit. And really what changes is the sign-off process that we talked about earlier. So extending the package designer's knowledge base from laminates into building wafers requires that additional step of formal verification. There's also very differing styles for routing interconnects, specifically around power and ground. On a laminate, it's typically a copper pour. On a silicon substrate, it's more of a rail-based type of routing environment. So, and also very, very sensitive around metal balancing or metal fill in these designs. And as the previous presenter talked about, also is design capacity. As you move into these very high pin count designs with lots of complexity around degassing and so forth, the number of instances in your design can grow beyond 1 million, and into the billion range. So it's important to make sure your tools can handle the capacity of these next generation of designs. Moving on to the last category. So these are the 3D-HI challenges coming from the ASIC or SoC design world. Again, can't overemphasize the need to be able to concurrently design across chiplet, package, and even PCB. Having a database shown in the yellow box here where you can bring in all the different chiplets from digital, analog, RF, photonics, wherever it might be, look at different packaging configurations, even look at different board form factors, and really be able to look at the design in a 3D perspective, which when you work across chip package board, everything's 3D. The board's one level, the package is another level, and the chips are another level. So it has to work in a 3D type of design environment. A big concern when moving to full 3D-HI is thermal. Thermal becomes the most critical thing when moving to full 3D integration, where you're using bumpless stacks to integrate cores on top of one another, or memory on logic, those types of flows. Thermal, it must be considered very early in the design process, long before you've done place and route. So you need tools that can use parametric data to describe a lot of the characteristics of how the die is or chiplet is expected to dissipate heat, and being able to model that early in the process. And then of course, having that and creating that golden sign-off net list. So if you're moving from designing a single ASIC, you're now designing a system which combines multiple chiplets and packaging. So you need an environment that allows you to create and optimize that interconnect or that net list across the different chiplets, and certainly through the packaging, and sometimes even on to the PCB. So that having that aggregation cockpit for that purpose of optimizing is critical when moving into the world of 3D-HI. Next set of challenges is really around implementation. We're now talking about integrating at the standard cell level, at the IP block level, even at the transistor level in the third dimension. So using that old model of abstract representation or black box representations of chips and chiplets will not fly. It does not work in this environment, because you need to do things like route restore sharing between the bottom die and the top die. You need to do Z directional placement. So you need to potentially, for thermal reasons or timing reasons, the ability to place in the third dimension. So if you don't have a tool that can support multiple tech lefts or multiple PDKs in a layout session, you won't be able to really optimize your design. You're working with more of a black box, and you don't have that flexibility of being able to move devices for various different reasons, not only in the 2D direction, but most importantly now in the 3D direction. And so of course you're looking, the timing driven routing, it becomes very important. Test was mentioned earlier. This is the time that you need to integrate the test strategies. There's an IEEE standard for 3D-IC where you put elevators in through the bottom and middle die to be able to test up into the very top die, kind of shown in the lower right there. But again, the big difference here is you're not doing buffer to buffer type of design like you would in traditional chiplet, where you're just using AIB or UCIe to connect things. That doesn't apply here. You're just connecting flop to flop in the 3D direction. So you just have a little RC circuit that represents the hybrid bond. So the packaging tools that have been used in the past based on abstracts are not applicable as you move into the world of true 3D integration. And then on the sign-off side of things, really it's a lot of the tools that you would use in the digital sign-off are required here with some additional capabilities. So closing on basically STA, static timing analysis. When we close on timing, we close across multiple process corners. So process variation, process device temperature, power, and so forth. There are multiple areas that we need to sweep across when closing timing. And the more chiplets you add into this design, the number of corners grow pretty significantly. So you need a static timing tool that can handle all that. You need the ability to again generate that net list to drive the system level LBS, which is often overlooked when starting up new designs. You need to look at concurrent loading or IR drop across multiple die in the stack. And one of the most important things that people often forget is you really need a very comprehensive way of checking the CMP planarity across two die that are going to be attached face to face. They have to be very, very planar in nature, otherwise they will pull apart. And so having advanced DFM tools to support that type of capability is very important. And that takes me to my last slide. So really the things that need to be considered in the next generation of tools for 3D-HI are, really an environment that supports not just digital and not just implementation, but all the way through top level planning and optimization, timing, system level LVS. Signal integrity now becomes important to chip designers because it's going chiplet to chiplet compliance, verification, early stage thermal and power that we talked about have to be part of this common environment. And then the whole world isn't digital. We have to be able to bring in optics and RF into this, and 3D stacks still sit on packages, and so do interposers. So the traditional packaging tools don't go away. They're just an additional tool. So the thing to look for is really all this capability and more. Test, for example, under a single common database type of environment that can handle very high capacity types of designs. And that kind of concludes things. So we're kind of, in this world of more than more based on 3D-HI, heterogeneous integrations, looked at multiple different packaging technologies, and there's a lot of new challenges facing design teams. And that concludes my presentation. Thank you.
Thank you, John. So a whole bunch of questions. When you talked about DRC, are there new things that are being done, to enhance 3D versus 2D DRC? So for example, when you have local design changes at one level in 3D, it can create thermomechanical challenges for the overall package structure. So, something might be locally good in a die, but you got to then look at the die above it or below it, so are the DRCs now looking in both the X, Y, and Z direction for?
Yeah, so today the typical DRC decks, so there's multiple ways of looking at this. So their DRC is done typically, while you're doing the layout, there's some DRC being done. And yes, there are some ways with the tools today to start looking at the design, in design sort of DRCs, but really it's important to be able to do the sign-off DRC. So in layout, that's one thing, everything's DRC clean, but then you generate Gerber or GDS data, and that's what's going to be used to manufacture the design. And that's where the formal tools for DRC and LVS come into play, is to validate that artwork, that manufacturing output. And there's discussions about having DRC decks that work in that sort of 3D-HI world, but a lot of it today is based on signing off on each individual chiplet at the artwork level, and then using tools like LVS to validate, for example, that they're aligned correctly through the stack. So there's, when you align micro bumps, they don't necessarily have to overlap, in the center of the pad, but there has to be, 80% coverage type of thing. So those types of rules are absolutely in play, but they're more, at least from our tool perspective, it's more on the LVS side of things that validate that third dimensional, what you're calling a DRC.
Okay, got it. This is just a comment, but you can agree or disagree. Question was, or the person was commenting, it appears that MCMs were 20 years ahead of their time. Or is a better way of looking at it, we're going back to the past, or multi-chip modules?
Yeah, I think hopefully that first slide kind of explained, but yeah, so multi-chip modules there's a lot of similarities when you do the type of chiplet designs that are out there today. That changes significantly, as I try to point out there, when you go to that level of 3D integration, where those MCM tools, again, used abstract representations of each die. right? You had the locations of the IO buffers or the pads. You had a signal name associated with that, the die extents, and that's what MCM designers use, is that abstract view to then create the substrate that connected them all together. And that is very similar to the world of chiplets today, although most chiplets are being integrated on silicon, so it's a little bit different. When you go to that world of 3D integration, we're actually folding macros on top of each other and folding circuits on top of each other without an IO buffer separating them. That's a different world. That's the real world of 3D-HI that I think we're heading towards.
Right. And you touched upon this, the concept of, not being able to do this with black box. So, for example, how much is a chiplet provider going to have to provide the other design team? So, in your examples, you showed like an HBM stack. I mean, are they going to need gate level details on that stack, or how much data do they need to be able to do the simulations and the checking of the overall design for each chiplet provider?
So with the world of where we are with today with chiplets, there's basically an IP block or a grouping of IP, and it's got a wrapper around it. Around that wrapper are little micro buffers that handle the signaling between the chiplets. They also handle test and ESD and other types of things. And then those buffer to buffer connections will be based on an AIB interface or a UCIe or an OpenHBI or a BO interface. And so it's then you're just like a PCB. You're validating that electrical interface between those chiplets meets your compliance, that there's not too much jitter on the signal, there's not too much noise on the signal, and you have enough design margin in there. So it become in the world of where we are today with chiplets, it's very much like a small PCB tool, and using tools we've used in PCB forever called signal integrity tools that allow you to basically extract that layout parasitic model. You put a driver receiver either in a HSpice or Spectre, or most people use a behavioral model, IBIS, for example, IBIS AMI, to characterize that. So what that means is the chiplet providers today just say, okay, this chiplet is based on BO, and so there's a spec that says, okay, I need to use the BO interface. This is how what the interface should look like from a physical and electrical perspective when I connect to the other device using the BO interface.
Okay, so basically you get the wrapper level, and everything inside the wrapper is a black box. So you can do your signal integrity, and maybe this is a question for one of the other presenters, but you may not be able to do your thermal simulations and things because you don't know how that chiplet is going to heat up, for example.
Yeah. So no, so there are thermal specifications. So there will, kind of to my 80K thing here. So we believe part of the design libraries for chiplets that will be part of this 80K will have thermal models and power models associated with that. So you don't have to give, down to the transistor level secrets away about that chiplet. But there are some thermal standards and power standards that will allow kind of an abstract model representation of that chiplet that can be used then by the system level thermal tools. So when you stack all these together, the system level tool, aggregates all those chiplets and does a system level thermal, through the packaging, through the board, which is going to be the biggest part of the heat dissipation system anyways.
Got it. Okay, so let's tackle one or two more questions. There's such a wide range of package options. Do you have tools or some framework to help designers pick the best way of packaging a given application? I mean, where do they start?
Right. That's a great question, and we're working on some things based on some government funding. So I can't talk about too much, but that's where design teams spend the majority of their design time. It's okay, I'm going to design, I'm moving from single die to the world of 3D-HI. where am I going to get chiplets? Who's going to provide those chiplets? I get what's going to be my best packaging choice. And it's going to be different for everybody. Someone who wants, cost is most important. Somebody else is going to say form factor. Somebody else is going to say rad hard. So the proposal here is really to have that part of this planning environment that we talked about here. So we already have this planning environment that works across, where did my slide go? Kind of shown here, where we work across chip, package, and PCB in this planning sort of environment. And that's in this environment that there needs to be a filter, basically a switch box, where the RF design team comes in, the digital design team, the system architect, and says, okay, I care about form factor, I care about cost, I care about weight, I care about whatever they're caring about. And from that, it would, in theory, filter this library of ADKs. So ADK, this is the future, but in the future, let's say for every packaging technology out there is an ADK. So this switch box would say, okay, come in here, this is my criteria, and it filters, your 200 ADKs down to 2 ADKs that are working with that. So that's all, that's all theory right now, in early stages of architecting that sort of solution that would also filter your chiplets by your chiplet library, right? Because that's the other piece of this is, okay, what's the best packaging choice here to minimize risk or cost, whatever it is. And then what are the best chiplets? This thing's going to go up in a satellite, so everything's got to be rad hard. And this kind of filter that the users would set would filter your chiplet library of 10,000 chiplets down to 15 chiplets that would work in that environment.
Based on requirements.
So the answer is that people are working, including Cadence, working towards this step, because we talk to design teams and they'll spend 6 months trying to figure out what is the best packaging choice for their 3D-HI. And it's different for everybody, because everyone has different requirements. In the defense industrial base, you're building something that's going to be used in a military application. If you're designing, some ultra high volume, something for in a smartphone that you have to, form factor is a big thing. Cost maybe not, but anyways, that's a work in progress.
Got it. And talking about design time, I mean, once a design team moves to the world of chiplets, 2.5D, 3D, I mean, what happens to their timeline? I mean, is this going to save time in the future, or is it's taking long? I mean, if and I don't know whether you want to say, hey, the average design takes N months. Right. Does it, where are we? I mean, that's
we're in the early stages, and if you're a company brand new to this, your first design is going to take longer, because you've got to figure all these things out. You've got to design some chiplets that you're going to use in the next. Once you've done one, you move the second one. Okay, I can reuse 2 of those chiplets. I know a little bit more about how I want to package. And so absolutely 3D-HI will, I believe, reduce design cycles in the long run as people get up to speed and get their chiplet libraries and their ADKs and every, part of the whole ecosystem starts to come together for them. Then the world of this modularized world where I can reuse all these different chiplets and don't care about what node or what technology they're built on is, that will absolutely shorten design cycles in the future. But the first, that first transition from single monolithic ASIC to this world of 3D-HI is, it's retooling, it's re-education, it's a lot of things. It's that are in some cases a one-time thing, so you learn from it, and the next generation will come along. Cadence is also working on some AI machine learning things that will also be part of this, selection process of the right package, and AI just gets smarter over time, right? The more you use it, the more data you feed into it, the more it learns, and that there again, that's some technology coming down the road here that's going to help a lot in this space.
So we'll leave one comment that you may want to reply to. The person here is saying, hey, I like the idea of having one tool for managing all these very complex system designs, but you still need a team of experts in all the different domains? I mean, does this, yes, it unifies the data and probably reduces the friction between the experts talking, but you still seem to need deep expertise in, let's say, half dozen different domains to pull off a design.
Yes, you certainly do at the sign-off level. So you still have to have a test expert. You still have to have a verification expert. You still have to have a thermal expert. You still have to have a signal integrity expert. You still need all those experts to sign off on the design. But a lot of these planning tools, you're kind of making estimates. You're making some guesses, and the tools are pretty good at making you seem smarter than you are by using parametric data and say, call up the mechanical engines there, and what kind of heat sinks do I have, and you can parametrically describe that in early stages before you've done place and route. And so there is some help at that architectural level to make it easier for a single person to do more work. But yeah, this I talk to people all the time. This moving in the world of 3D-HI doesn't mean everyone's job gets easier. It doesn't. There are more tools in the flow, and the tools are great, but there are a lot of them, and a lot of expertise is still needed because you're really merging the world of semiconductor design with the world of system design into a single environment. And historically, chip designers do their thing, and system designers doing their own thing, and this is really about that world kind of colliding, those worlds.
Great. Thank you very much, John. An excellent presentation. I want to once again thank our sponsors, Advantest and ASE Group. Advantest receiving the highest customer ratings in the annual VLSI Research Customer Satisfaction Survey for 2 consecutive years. And ASE Group, the chiplet era has begun, and helping drive the solutions in packaging and test to deliver these advanced packaging technology to make heterogeneous integration a reality. So I thank both the sponsors for making the event possible and free of charge to everyone. And I most importantly thank all of you for spending the time with us. Hopefully you've enjoyed the presentations, and I'd like to thank the presenters once again and wish everybody a good day. Thank you.